go. Okay, foundation models. What do you think? Who thinks these LLMs, foundation models, whatever you want to call it, are really awesome and like the key to all of our solution, or key to all of our problems in the future? Who's maybe skeptical? A lot of skeptics. Okay, awesome. Well, we'll see what you think by the end here. So, what I'm going to be talking about today is not foundation models for language modeling like ChatGPT and its cousins, but foundation models for Earth and space exploration, and particularly using remote sensing data. So remote sensing satellites are these amazing human inventions that we've had orbiting our planet Earth since 1972 or earlier, depending on what kind of satellites we're talking about, and collecting continuous data about what's happening on our planet and happening on other planets. So we can get so much information without even physically visiting these places. It is really an incredible resource. And almost all of that data is publicly available for free. And this data has huge potential for helping us to get information that we need for small scale problems on local, your neighborhood kind of scale, as well as really large scale problems across the entire planet or even our solar system. For example, on Earth, one of the projects in my group is using remote sensing data to estimate how much food is being produced in different places, including in Sudan, and what the impact of extreme events like wars or the civil war in Sudan has had on food security to help with famine early warning. And of course, we have these satellites not just around Earth, but around other planets, especially Mars and the Moon. We have quite a bit more than anywhere else. And this gives us a huge amount of information and reconnaissance that we need to understand what has happened on these planets in the past and present. So for example, some projects we're doing in my group in this area are mapping pitted cones across the global surface of Mars to help scientists understand the water history of Mars, and mapping craters and other kinds of features to help with better hazard navigation and answer other planetary science questions. So all of this is enabled by a huge amount of data, but everything that I've talked about so far has been using something called supervised learning in machine learning. Who is familiar with the term supervised learning? Okay, so supervised learning is how often we learn as humans, but it requires something called label data. So it requires that somebody has annotated what the answer is or what we're trying to find in some data. So somebody has looked at this raw satellite data and said, here are where crops are growing in Sudan, and we can train models to find all of the other crops in Sudan, or the same for craters or any other feature. And historically, this lack of labeled data, which takes a huge amount of time to annotate, and as you can imagine, a lot of the things that you as scientists might want to find are not things that you can just hire a random person on Amazon Mechanical Turk to label. It requires expert knowledge. And so annotating that data can be really expensive and take a really long time. So historically, this has been the biggest bottleneck to using machine learning for remote sensing data. And this kind of supervised learning, again, is where we take this data, maybe we have some training examples of galaxy observations, and somebody wants to automatically classify the types of galaxies. And they go in and label 1,000 or 10,000 or whatever examples of these are spiral, these are elliptical. And then we train the model by saying, okay, you got that right, you got that wrong. And the model is trying to minimize its wrong frequency. But again, we are very limited by this labeled data, but something that has changed in recent years in language modeling, in machine learning, and really completely upended the field of machine learning has been saying, well, what if we don't need labeled data? What if we can just learn from the data itself? So actually looking at language data that has not been annotated to say, you know, oh, this is a positive movie review, or this is an English sentence, or whatever the supervised labels might be, but just saying like, this is language, and we will learn the structure of it. And that is really a game changer for machine learning because it allows us to tap into these huge data sets that would otherwise be kind of unusable in a supervised learning paradigm. And so if we then think about remote sensing data, we have actually a huge amount, petabytes and petabytes of unlabeled data. So if now we can look at it with this lens of not needing labeled data, then maybe we can do something completely different and really change the game in remote sensing with machine learning as well. And we think about large language models being trained on a large amount of data, but in terms of remote sensing data, that data size is like piddly. It's a drop in the bucket compared to what we have. So ChatGPT, the model that ChatGPT was based on, GPT-3, was trained on only 45 terabytes of data. And that's basically less than what Earth satellites collect in a single day. So we have an incredible amount of unlabeled data at our disposal. So the way we can learn from this data, you might be thinking like, okay, I kind of see how you could learn from these labeled examples to do a task, but how do you learn from unlabeled data? And what are you really learning? So what we do here is called self-supervised learning. So the idea is that we're not learning from like an external label, but we're trying to learn to predict the characteristics or the content of the data itself. So in the case of these galaxy observations, maybe you have all these examples, and then we have what we call a pretext task for training. So it's like a fake task, basically. If you think about like if you're studying with flashcards or Duolingo or something and you're covering up a word and trying to predict what the word is, or translating a sentence, or somehow masking something out in order to predict what was there, that's what we call masked reconstruction. So that is a very common pretext task where we would take one of these images and randomly cover up pieces of it, like you saw in our Blinky slide, and try to predict what the content was that's missing. Another common pretext task is contrastive learning, where we take pairs of things that are similar and pairs of things that are different, and we try to minimize the features that a model's learning between the similar pair of examples and maximize the distance between the different pairs of examples. And those pairs could be things like images of the same location or the same galaxy from different satellites or different telescopes, or maybe images taken at different dates. Really, we have the creative flexibility to construct whatever kinds of pretext tasks we think will be helpful for learning the content of these data sets that we want to train the model on. So for large language models like GPT, we are doing self-supervised learning. These are trained with self-supervised learning algorithms. Does anybody know what GPT stands for? Pop quiz. Any guesses? It's amazing. Nobody ever knows, even though we say it all the time. I would like to hear a guess first, because I'm a professor. What was it? General purpose something. Okay, good guess. All right, it is a generative pre-trained transformer. So that is what GPT stands for, obviously. So generative pre-trained transformer, the pre-training is this self-supervised learning that we've talked about. A transformer is the type of architecture of the model, so kind of the function structure. And generative is describing the fact that it's predicting something new. It's not like classifying something or describing something, it's predicting some content. So the pretext task that GPT is trained on is called next token prediction. And a token is just a word here. So what GPT has been trained to do is basically take all of this data on the internet, every page available online. It's in a data set called Common Crawl, and including the ELSI website, and create like infinite examples of sentences where we've masked out the last word or the last token. So we can take bits of these sentences and turn them into these self-supervised training examples. So the goal is to take whatever previous words, like ELSI's mission, and predict the next word. So ELSI's mission is, for example, and so on and so on. So you can see how in this way we can create infinite examples to train a model on without ever having to label this data ourselves. And so after training the model on all of these examples across the entire internet, now we have a model that's very good at predicting the next word. That's why when you use ChatGPT, you see one word come up at a time. It's always predicting the next word based on the previous words. And that's all it's doing. And then amazingly, it can learn structure of data, language that way. And then we can take this general model, really is general purpose, it would be another good name for GPT, and fine tune it, so further train it on specific data for lots of other tasks like Python code completion. Many of you might be using GitHub Copilot or something similar, or ChatGPT, chatbot responses, language translation, whatever it is. So that's what foundation models are these general purpose models that we've pre-trained in a self-supervised way on some very large corpus of data, unlabeled data in particular. And then when we go to use that model for something, it's not really useful as it is, it's just generic, but then we'll use it for a specific purpose by fine-tuning it for maybe some new classification problem, or just using the features that it's learned for visualization or something. So, okay, that's great about ChatGPT or language models and everything, but how are we going to use these foundation models for Earth and space exploration? We're not modeling text here. We can't just use GPT as it is for the kinds of tasks that people in this room want to study. So we don't want to talk about LLMs. Maybe we want to talk about large Earth models or large Mars models or large planetary models, where we want to have these models that have been pre-trained on this diverse, huge corpus of data that we have from remote sensing and all these different instruments, and be able to fine-tune that generic model for our specific tasks, like in agriculture or geology or marine science, whatever it is on Earth, or for Mars or other planetary science domains. Instead of having these situations where a team of planetary scientists has a goal that they want to study, maybe understanding where ice is on Mars, looking at dust devil tracks or gullies, and having to each annotate their own data set of tens of thousands examples to be able to do supervised learning and then train their custom machine learning model, which is what people have to do right now if they want to use machine learning, which is extremely costly. Instead, we want to be able to take one of these general purpose models and start with that and just show a few examples of what it is you want to find, and then the model will quickly adapt to that. And so people are developing these kinds of foundation models for Earth and space exploration. And there's getting to be a lot of hype, but also popularity around this, and a lot of promises being made. For example, NASA has been tasked to create a foundation model for every NASA science division. So heliophysics, astrophysics, planetary science, and earth science. But is anybody using them? No. So there's a lot of development happening, but not a lot of real world use of these models happening yet. And I claim that a lot of this is due to the fact that remote sensing data is completely different than the kinds of data that we typically use in machine learning. So, ChatGPT and DALL-E, the image kind of variants, are all developed for natural language or for these kind of consumer images like those that we take on our phones. They're using data sets that have been created from Flickr and social media websites. These data are so different than what we have in remote sensing. In remote sensing, we have the temporal dimension with incredible amounts of change. We have so much variability in the spectral dimension. We have completely different spatial structures of the subjects that we're imaging. And so historically, a lot of researchers have been kind of lifting and shifting these approaches from computer vision and just trying to apply them directly to remote sensing data, and really getting pretty mediocre results because of that. So if we want to create foundation models that are better aligned to the kinds of patterns that we see in remote sensing data, we need to think about what are these unique aspects of remote sensing data that we want models to be able to capture. So for example, in remote sensing on Earth, for example, we have many, many, many complementary sensors. We have optical sensors, radar sensors, all kinds of things. And we also have all of these derived products that people have been creating for decades, like forest height maps or land cover maps, elevation maps, DEMs, all these different things that are just available to learn from. And on Earth, we collect, for most data sets, these data everywhere. So we have complete coverage over the entire Earth for most of these satellites and derived products. And for most openly available remote sensing data, it's not, again, this is a difference between kind of consumer photographs and remote sensing data where we're not like zoomed all the way into a single subject. Like if you think of the image of a face and you're trying to do some facial recognition or detect that there's a face in an image, it's important that you have this kind of receptive field over the whole image for the model. So you need to be able to see like there's an ear here, there's an eye here, there's maybe somewhat symmetry. You want to have this global context over the whole image. But for remote sensing data, it's not always helpful to have that. You don't need to know like, oh, there's a forest here, so that probably means there's a lake over here. It's not a thing. So that means that we actually don't usually need very deep networks, where in the word deep neural networks, that depth often gives us a wider receptive field, visual receptive field, but we really don't need that for remote sensing data. And again, like I said, in remote sensing data, there's a huge amount of information in the spectral and temporal dimensions that these traditional computer vision approaches are just completely not considering. So if we're lifting and shifting those approaches, we're missing out on most of the information that we might have. So in my group, when we set out to create a foundation model for Earth observation, we had this driving criteria that we wanted to actually capture the important aspects of remote sensing data, but in particular, we wanted to create something that was actually usable right now, that people who are using Earth observation data to map different properties or phenomenon across Earth could use immediately. And so the model that we developed is called Presto, the pre-trained remote sensing transformer. And it is a masked autoencoder. So its pretext task is masked reconstruction, which I described earlier. So it gets an input example, some observation of the Earth, and we mask out parts of the image or parts of the observation, and the model tries to predict what the missing pieces are. And then once that model is trained, we take Basically, it encodes that input into a latent space, into some lower dimensional subspace, and then it tries to predict what was missing based on just that low dimensional representation. That's what an autoencoder is. And then once the model has been trained, we throw away the decoder part. We no longer want to fill in gaps of things, although you could. And we just use the encoded representation, these generic feature extractors, to do these downstream tasks, like for this task-specific fine-tuning. So Presto is trained with not just one satellite input, but many satellite inputs. We have optical remote sensing data, radar data, precipitation, temperature, land cover maps, kind of everything but the kitchen sink thrown in there, the location, where the image was taken, what time it was taken, et cetera. And we have a time series of all of those, so a time series over an entire year. And when we do this masking for the reconstruction, we're not doing it randomly. We're doing it in a structured way that's based on the kind of missing data that we see in remote sensing. So we want the model to be robust to missing data when it's deployed. And so we will mask out an entire sensor, for example. So we'll say, okay, you have to predict the optical observation based on everything else. Or we'll mask out parts of a season. So we'll say you only have the first 6 months of data, predict the remaining 6 months. So we call that structured masking. And so that way, when the model is being used, you don't need to have all those instruments. You could just have one or a few. And we use time series, like I said, and just not these large images, but just a tiny patch, a single pixel of imagery, which helps us keep the model very small. And we sample the data using a stratified sampling across the whole world that tries to maximize the diversity of landscapes that the model has seen during pre-training. And then when we go to test how well this model works for lots of different tasks, we tested it on several different downstream tasks in agriculture, tree species classification, land cover mapping, wildfire fuel moisture estimation, algae bloom, regression, that all have like a different shape of the data, different number of time steps and sensors available, different number of training examples available for that fine-tuning to the specific task, different types of tasks like classification, regression, segmentation, and in many different places in the world. And we show that Presto performs competitively to or better than the previous state-of-the-art models, even though it is 1,000 times smaller than those previous models. And it being smaller makes it way more accessible to end users. So our end users don't need 8 GPUs to use the model like they do in some of these previous ones. They can just fine-tune the model on their regular MacBook or PC, whatever it is. So for all of these reasons, it's led to Presto being adopted by many different end users, not just us in my own group, even though we do use it for some of these other tasks that I mentioned. But the ESA World Cereal Project, which is creating global maps of cereal crops every season over the entire world, has integrated Presto into its pipeline. So you can go to ESA's website and use Presto in their infrastructure now. And we've worked with many other people who have adopted Presto in commercial companies like Regrow Agriculture, or Floodbase for flood mapping. Allen AI Institute is using it for wildfire fuel estimation, species distribution mapping at JPL and other places. So lots of different end users have adopted it. So when we were successful in creating a model like this for Earth, of course we wanted to be able to do this for planetary science use cases as well. So for Mars, we don't have as much data as we have on Earth, but we have a lot of data, and we have a lot of planetary scientists who want to be able to, make global maps of features that they're interested in, or use these kinds of models for hazard avoidance or terrain navigation, things like that. So we are funded by JPL in collaboration with the Machine Learning Instrument Autonomy group there to create a large Mars model, or try to investigate if we could develop effectively a foundation model for Mars orbital data. And the kinds of tasks that we are evaluating the model based on here are kind of key, what they call at JPL infusion targets, but key kind of priorities at JPL where they want to be able to integrate machine learning into existing missions or science investigations. So there's a project for mapping global Martian frost at JPL, and so that's one of our evaluation tasks. On the planetary data system imaging node, if any of you have used that, you might have noticed there's a content-based image search, so you can search for images that have craters or that have dust devils or whatever, and that's what this high-rise landmarks data set is based on. And we have another data set that's called DoMars 16, which is in CTX rather than the high-rise sensor, of lots of different Mars features. And so when we set out to develop this model, at first we thought that we might do a similar approach to Presto, where we take, high-rise CTX, Themis, whatever other Mars satellite observations, and stack them all together at the same place and train a masked autoencoder. But when we thought about it, there are some similarities between Mars and Earth remote sensing data sets. Like, there's a lot of different sensors that we want the model to be able to ingest. We want it to perform well globally. We want it to be computationally efficient, but there's also a lot of differences between the two. So on Earth, we have all these different shapes that the model might need to ingest, like images or time series or image time series. But for Mars, most people are looking at rasters, just at images. They're not usually looking at time series. There's not a lot of dynamic change happening on Mars to need that kind of monthly time series like we had on Earth. On Earth, we have like hundreds of sensors, but on Mars, we have relatively fewer, on the scale of tens that we want the model to use. And there's not coincident coverage everywhere on Mars like we have on Earth. There's kind of sparse coverage or different coverage of different satellites. And on Earth, these satellites we're looking at usually have a pretty similar scale range, like 10 to 60 meters per pixel. But on Mars, it's extremely wide. So it'll be like centimeter scale to 500 kilometer scale that people want to look at. So stacking images together of the same place really doesn't work when you actually try to implement that. And also, there's a huge amount of sophisticated compute resources for Earth observation and computation, but that community is extremely limited in planetary science. So we had a really limited set of tools that we could use for creating these data sets. So again, with Presto, when we did this kind of stacking of coincident observations, this really wasn't the approach that we could use for multimodal learning on Mars. So what we decided to do is a really cool approach where we train individual models, individual masked autoencoders on each of these sensor data sets. So Themis, CTX, HiRISE, whatever else we want to do. And this is going to sound crazy, but we actually just add those together. So you take these model weights. These are all basically, think like y equals mx plus b for each one, m and b being the parameters, but like way more of those, millions or billions instead of 2. And we literally add those functions together. And that allows us to have a single model that can take in any of those observations, but has kind of the internal circuitry to parse each of them individually. And that sounds really wild, but there actually is some theory behind this. This is based on a paper that came out several years ago called Task Arithmetic that showed that you can actually add and subtract and analogize models to be able to gain or lose different capabilities. So long story short, with the results, when we evaluated our pre-trained model on these different tasks that I mentioned, we found some really interesting things that where you train the model on only, like you take the pre-trained model and you show it more CTX or high-rise data, so just individually one of these instruments, then the model actually gets worse than if it didn't see any Mars data at all on one of the tasks. And if we train it on both CTX and high-rise data, it also gets worse. But if we train the model on CTX images and high-rise images and add those models together, so literally the only difference between these rows here is we've added this plus this, the model coefficients, you get a huge improvement on the performance of those tasks. So basically we've shown this is a really effective way to gain multimodal capability with these models without training a model on all of the data. So our next step is to prove the theories behind this and scale it to larger models and larger data sets and make that available to planetary scientists. So I'm getting the bell, so I'm just gonna leave everybody with these closing thoughts. Coming back to the title of this talk, Foundation Models for Earth and Space. Are these the key to our AI applications for Earth and space exploration or distracting hype? Maybe both, I would say. I think there's a lot of great things we're doing with them, but we have a long way to go. And it's just gonna be hype if we just continue to try to lift things from computer vision without thinking about the specific science domain. And that means computer scientists like me have to work closely with planetary scientists and earth scientists to develop actually useful things. Another more meta question for people to think about is like, some of you might be surprised that all ChatGPT is doing is predicting the next word. And you're like, how are these models gaining such complex, seemingly complex or sophisticated understanding when they're trained on such simple tasks? And then I just ask a question back to that, which is like, what is intelligence? What are humans doing? Are we just predicting the next word? And something fun I thought from one of the talks yesterday was a really key thing about both what humans are doing and what these models are doing, and I guess what biological systems in general are doing, is compression. So finding these dimensionality reduction mechanisms, that is essentially what these models are doing effectively. So food for thought. Thank you.